Welcome back to another episode of the Dish TV. I'm Renita Malhotra-Hora, Head of Marketing and Communications at SRI International. And I have with me today Jesse Wodin, who is Lab Director of Applied Sciences here at SRI. Hi, Jesse.
Hi there.
So, Jesse, Applied Sciences, this is a lab that covers so much, a wide variety of topics: sensing, communications, quantum sensing, chemical sensing. Make some sense of that for us. What does all of this mean? Give us an overview.
Yeah, so we tend to think a lot about how information flows through the world and how we can sort of better detect, sense, read out that information for all the stakeholders we work with. So that could be building better communication systems, building better sensing systems for aircraft, for cars, for people. And that's sort of the general mantra that we go after.
What are these technologies? When you say communications and sensing, are we talking on ground, above ground, below ground?
We work all over the place. We work on underwater systems, underground systems, air systems, systems in space, systems kind of in cyberland, kind of all over the place. So we develop generally kind of early stage and to mid stage technologies in all those domains, in the areas of things like navigation and timing systems, so cars to drive around by themselves, radar systems, RF communication, optical systems. We do quantum sensing, which is using principles of quantum mechanics to sense the world around us, and chemical sensing. So it's a lot of different areas.
You're right. It's a lot of different areas. And I wonder if we could actually break them down, maybe one by one. Take me through them. RF, you've mentioned RF sensing, quantum sensing, chemical sensing. Step by step, what are these?
Sure. So for example, navigation and timing systems, that was one of the first ones I mentioned. So the GPS, the Global Positioning System, is a set of satellites that surround the Earth. It's run by the US military. The services are available to everyone on the planet. That provides navigation information to everyone. Your cell phone has a GPS receiver in it, receives radio signals from those satellites. Your cell phone, the cell phone infrastructure, power plants, lots of stuff also receives timing information from that system. So those are satellites in space, and everyone's a little bit worried that satellites will get taken out by space weather or something to go wrong. It's hard to go up and fix the satellite. So for example, we develop technologies that will allow navigation systems or timing systems to keep operating, so the electrical grid doesn't go out. So radar is, used by aircraft to detect other aircraft so they don't crash into each other, for example, or for boats to detect other boats and things like that. So one thing we do, because we mostly work for government customers, is we develop really quiet radars. So radars that are pretty hard to sense the signal. They kind of look like noise. So in that case, we have sort of government customers who are very interested in radars that are just whispering. And then there's optical and RF communication. So we deal a lot with communication systems. So radios talking to each other, networks of radios, Wi-Fi systems, but also increasingly now optical systems in space. So these are satellites talking to each other. So now we're entering the domain where there's going to be thousands and thousands of satellites in individual sort of clusters, all working together in concert. They have to all talk to each other. The way that they are going to talk to each other is with laser communications between the constellations. So we work on the architectures behind that. And then the last two I mentioned were quantum and chemical sensing. So quantum sensing is utilizing atoms and light that interacts with those atoms as a tool. So if you can specially prepare strontium atoms or ytterbium atoms or something in very specific ways, you can use them to sense the world around us. So magnetic fields from your brain, or magnetic fields from underground, or radio frequency signals that are very weak, or very weak optical signals, things like that. So we develop new sensors that use those techniques. And then finally, chemical sensing. Part of our group is developing sort of an ultra small, which is still about this big, very sensitive mass spectrometer. So that's a device that measures very small chemical signatures. So it can detect, pollution or, possible chemical sensors from bad actors and things like that.
I'd love to ask you a little bit more about quantum sensing. I think the word quantum is holds a lot of interest, but nobody really understands kind of what it means, and quantum sensing being a subset of quantum research, quantum physics. You talk about light and atoms coming together, and you talk about creating magnetic fields, for example, those in your brain or underground. Now, those seem to be a whole lot of different things. So help me understand.
Sort of the field of quantum sensing is based on what's called quantum mechanics. So quantum mechanics is an area of physics that was really kind of came into being in the 1920s. So people have been thinking about it continuously since then. Many textbooks and papers and conferences on the underlying science of quantum mechanics. So quantum mechanics is the study of the physics of atoms. So atoms and molecules to some extent. So in particular, how atoms interact with each other and how light interacts with atoms. From there, you can build up a lot of physics. A lot of physics is just based on all of those theories, which have been shown time and again to really represent reality. So for some decades now, people have realized that not only is this science just showing us how the world works, you can actually use it to build tools. By understanding all the physics of these atoms and light interacting, you can sort of come up with ways to combine atoms and lasers together up until now on sort of large laboratory scales, and actually sort of sense the world around you. So detect the Earth's magnetic field, detect the magnetic field from your brain. Those are example of kind of detecting electromagnetic fields. Another thing you can do is detect what are called inertial fields. So this is detecting gravity, Earth's gravity. But then you can detect the gravity from, a person 100 meters away. Or you can say how fast you are accelerating. So you can sort of think, and then you think, well, I could build an inertial navigation system. I could build a core module for an airplane that tells me how fast I'm going. Or I could build a system that could actually very finely scan the magnetic fields from your brain. And then maybe I could use other techniques to understand what's happening in your brain. So things like that. So the reason why quantum sensors, so sensors based on quantum mechanics, is so interesting is that the realizable sensitivity of these sensors is unbelievable. I mean, you can't build a sensor that is that sensitive any other way. So it is the most sensitive way that we know to build something. So measuring tiny fields from your brain, you can do that with quantum sensors. It's very exciting, and the field has kind of exploded.
So in the next, let's say 5 years, 10 years, would the focus be entirely on these different areas that you've mentioned, or are there innovations, that you have in mind that you could share with us that you haven't told us about?
We made a corporate IRAD presentation to detect radio frequency fields with atoms. So radio frequency fields, these are things like TV stations, radio stations, your Wi-Fi router, your cell phone, satellite systems, all information going through the air is radio frequency information. So we have this idea that you could actually, instead of sort of building an antenna with a piece of metal, which is how it's been done for about 100 years, you could actually use atoms that are trapped in a little cell with lasers and stuff to actually build a very sensitive radio receiver. So the idea had been published already. I mean, people have been thinking about this for a while, but no one had really tried to kind of really build it and get it to work and measure all the details that you need to actually do this. So we pitched a corporate IRAD, an internal research and development program, and we won it. That allowed us to actually make a working prototype. It was big. It was on a table. It was had a bunch of lasers and power. It was a lot of stuff. It was not small, but it worked. That then allowed us to propose the idea to the government and get funded to do that kind of work at a much larger level.
Well, so we're actually building those systems now.
Yeah, that's right.
Amazing. That's amazing.
Yeah, it's uncharted territory at this point, so it's a lot of fun.
And it's also particularly exciting for, an incoming researcher to understand that they have this opportunity here at SRI to be able to come up with this kind of idea, pitch it, get funding internally, and then, expand it.
That's absolutely the kind of place SRI is. I mean, your career here is what you make of it. We hire in our group, we hire independent thinkers. We hire people who want to come in and make their way. You have to be a team player. There's a lot going on. You need to be able to work on each other's programs. I work on the programs for people who work for me all the time, and they task me to do work all the time. I wouldn't do that in a different way. But yeah, if you come in, if you have ideas, if you can develop them, there are resources available to do that. And you can, it's kind of endless.
Jesse, thank you so much for joining us on the show today. It's always a pleasure to speak with you.
Thank you very much.